In this video, let us discuss polarization in dielectrics. The basic difference between dielectrics and conductors is that dielectrics will have less number of electrons, free electrons, compared with the conducting material. Consider a dielectric molecule with positive charge plus Q nucleus and negative charge minus Q electron cloud as shown in the figure. To see the effect of electric field on dielectric materials, consider the dielectric molecule as shown in figure. If we apply electric field E bar onto dielectric material, the force on positive charge is F bar plus equal to Q E bar, which is along the direction of electric field E bar, and the force on negative charge is E bar equal to force on negative charge is F bar minus equal to minus Q E bar, which is in opposite direction of F bar, which is in opposite direction of E bar. After applying electric field E bar, charge is displaced as shown in the figure. The charge displacement is equal to sum of the original charge distribution and dipole moment with dipole moment P bar equal to Q D bar as shown in the figure. The dipole has the dipole is defined as the two equal charges with opposite signs are displaced by a small distance as shown in the figure. After applying the electric field, basically we get dipoles, and hence the dielectric material is said to be pole-wide. Such dielectric material is said to be non-polar. Example for non-polar dielectric examples are hydrogen, oxygen, nitrogen, and the rare gases. Other types of molecules such as water, sulfur dioxide, and hydrochloric acid have built-in permanent dipoles that are randomly oriented. So creation of dipoles by applying electric field to the dielectric material is known as polarization. Suppose n number of dipoles are formed within delta V volume, then the total number of dipole moments can be written as Q1 D1 bar plus Q2 D2 bar plus and so on Qn Dn bar equal to summation k equal to 1 to n Qk Dk bar. Polarization is defined as dipole moment per unit volume of the dielectric, whose unit is coulomb per meter square. So P bar equal to um, limit delta V tends to infinity, delta V tends to 0, summation k equal to 1 to n Qk Dk bar by delta V coulomb per meter square. Polarized surface charge density rho Ps equal to P bar dot An bar. Rho rho V equal to del dot epsilon naught E bar minus P bar. So rho V equal to del dot E bar del dot epsilon naught E bar plus del dot P bar. Rho V equal to del dot of epsilon naught E bar plus P bar. Rho V equal to del dot D bar, where D bar equal to epsilon naught E bar plus P bar. The electric flux density D bar in free space is epsilon naught E bar, that is P bar equal to 0 in free space. From the above equation, we can say that D bar is getting increased by P bar in dielectric material. From the discussion on polarization of P bar is directly related with the electric field E bar. Therefore, P bar equal to X E epsilon naught E bar. P bar equal to X E epsilon naught E bar, where Xe is the electric susceptibility. The value of parameter Xe gives how susceptible the given dielectric material to the applied electric field. So from which dielectric constant can be derived as So d bar equal to epsilon naught E bar plus xe epsilon naught E bar equal to epsilon naught 1 plus xe into E bar epsilon naught E bar equal to epsilon E bar, where epsilon equal to epsilon r equal to epsilon by epsilon naught equal to 1 plus xe, where epsilon is the permittivity of dielectric material, epsilon naught is the permittivity of free space, epsilon r is the dielectric constant or relative permittivity. Dielectric, the dielectric uh, the dielectric constant epsilon r can be defined as the ratio of epsilon to epsilon naught. If electric field strength is more such that it pulls the electrons from the outer shells of dielectric molecules, then the dielectric material becomes conducting material and we can say dielectric material has been broken. Therefore, dielectric strength can be defined dielectric strength can be defined as the maximum electric field with which dielectric material can tolerate or withstand. Dielectric strength can be defined as the maximum electric field with which the dielectric material can tolerate or withstand.